Imagine a universe where temperatures swing from the unimaginable heat of trillions of degrees, capable of melting matter in an instant, to the silent chill of near absolute zero, where atoms barely move and time itself seems to stretch in frozen stillness. Picture standing at the edge of a supernova, watching stellar matter explode with a force that outshines entire galaxies. Each particle a blazing inferno hotter than the core of our sun, yet just a few light years away. The vast emptiness of interstellar space lies almost completely frozen, its temperature hovering just above absolute zero, a dark, silent ocean of cold that stretches for billions of kilometers. This is the universe of extremes, a place where opposites coexist, where the fiery hearts of stars burn with unimaginable energy. And yet the cosmos also holds regions so cold that time itself seems suspended, waiting patiently for a spark of energy. In the next moments, we will embark on a journey across this cosmic spectrum, from the mind-shattering heat of colliding neutron stars, which briefly generate trillions of degrees in bursts of gamma radiation, to the meticulously controlled laboratories on Earth, where scientists have slowed atoms to billionths of a degree above absolute zero, creating a strange state of matter known as a Bose-Einstein condensate, a quantum dance so delicate it can only exist under the most precise conditions. You will witness the violent birth and death of stars, the furious collisions that ripple through space-time, and the silent, almost spiritual stillness of the coldest places known to science. But this journey is more than a spectacle of temperature. It is a story of how the universe tests the boundaries of physics, challenges our imagination, and illuminates the hidden order behind apparent chaos. Every particle, every photon, every atom is a messenger, telling us not only where the cosmos has been, but also hinting at the forces that shaped it. From the intense pressures that forge elements in stellar cores, to the gentle whispers of cold that preserve the primordial memory of the Big Bang. As we navigate this landscape of extremes, you will begin to understand why scientists risk their lives on telescopes, perched atop mountains and in laboratories cooled to near absolute zero, all in pursuit of answers to questions that have echoed since the dawn of human curiosity. How hot can the universe get? How cold can it sink? And what do these extremes reveal about the fundamental laws that govern everything from the tiniest quantum particle to the vast expanse of galaxies? Prepare yourself for a voyage where imagination stretches to the edge of comprehension, where the violent and the serene coexist, and where the very notion of temperature becomes a lens through which we glimpse the astonishing diversity of the cosmos. In this story, fire and ice are not just opposites, they are the rhythm of existence, the pulse of a universe that refuses to stay still, demanding that we watch, wonder, and explore. So, as we begin, open your mind to extremes that defy everyday experience. Suspend your assumptions about heat and cold, and get ready to step into a realm where the cosmos reveals itself in its most dramatic and delicate forms. From temperatures that can obliterate matter to realms so cold that even light struggles to move, and let your journey into the universe of extremes begin. Imagine standing at the heart of a star, where unimaginable forces compress matter to densities millions of times greater than anything on Earth, and temperatures soar to millions of degrees. Here, in the nuclear furnace of a stellar core, hydrogen atoms collide and fuse to form helium, releasing energy in a relentless blaze that fuels the star's radiance for billions of years. Each fusion reaction is a tiny explosion, but collectively, they form a supernova-scale furnace. A process that has been ongoing since the dawn of stars, producing the elements that make up our very bodies. Visualize the sun, calm to our eyes, but within its core. The pressure is so immense and the heat so intense that every second trillions of nuclear reactions occur, each releasing bursts of energy that eventually reach us as the gentle sunlight warming our planet. Now, magnify this by orders of magnitude and consider massive stars. Tens or even hundreds of times the mass of our sun, their cores reach tens of millions of degrees. And when these stars exhaust their fuel, their death throes produce temperatures that are utterly incomprehensible. A supernova eruption sends out shockwaves that compress surrounding matter, creating heat so intense that atoms themselves are torn apart into a soup of subatomic particles, gamma rays, and neutrinos. For a brief moment, these dying stars shine brighter than entire galaxies. Their ferocious energy broadcast across the universe. Yet their fury also seeds the cosmos with the heavy elements iron, gold, uranium, that will one day form planets and life itself. Beyond stars, there are even more extreme events. Neutron stars. The collapsed remnants of supernova contain matter so dense that a teaspoon would weigh billions of tons. And when they collide, the resulting temperatures can rise to trillions of degrees, releasing energy in gamma ray bursts that flash across the cosmos in seconds. In these collisions, matter reaches states never observed elsewhere, behaving in ways that challenge our understanding of physics, where quarks and gluons, the building blocks of protons and neutrons, may exist in a free, liquid-like plasma. Imagine witnessing the raw power of a black hole devouring matter, a process so violent that in falling gas is heated to millions of degrees before crossing the event horizon, emitting X-rays and creating jets that shoot across space at nearly the speed of light. Each of these phenomena represents the extreme upper limits of temperature in the universe, realms so hot that they defy human intuition. Yet these extremes are fundamental to shaping galaxies, driving chemical evolution, and creating the conditions for planets and eventually life to exist. These violent and scorching events dominate the universe's most energetic landscapes, yet they coexist alongside the most frozen, silent regions imaginable, revealing the extraordinary range of temperatures that the cosmos encompasses. As we shift from the furious heat of stars and stellar collisions, imagine descending into the opposite extreme, where temperatures approach the limits of absolute zero, a place so cold that atomic motion nearly ceases, and the very concept of heat becomes almost meaningless. In the vast voids between galaxies, matter is sparse. In the cosmic microwave background, a faint relic of the Big Bang lingers at just 2.7 degrees above absolute zero, bathing the universe in a ghostly uniform glow. Here, the universe is a frozen canvas, stretching for billions of light years, almost perfectly still, yet carrying within it the encoded history of the cosmos. In these regions, particles drift so slowly that quantum effects dominate their behavior, and time itself seems to stretch in this silent expanse. On Earth, scientists have recreated such extremes in laboratories, chilling atoms to billionths of a degree above absolute zero to produce Bose-Einstein condensates, a bizarre state of matter where individual atoms lose their identity and behave as a single quantum entity, flowing without resistance and demonstrating phenomena that challenge our classical understanding of physics. Picture clouds of ultracold atoms suspended in laser traps, glowing faintly as researchers probe their movements, revealing quantum vortices and interference patterns that look almost supernatural, yet obeyed the precise rules of quantum mechanics. In interstellar space, these cold regions act as incubators for new stars, where molecular clouds slowly collapse under gravity, cooled by radiation to near absolute zero, forming dense pockets that eventually ignite as stellar cores. The contrast between these silent, frozen expanses and the blazing fury of stellar explosions is staggering. Yet both extremes are necessary for the cosmic cycle of birth, evolution, and death. While one end of the spectrum demonstrates the raw energy and transformative power of heat, the other shows the subtlety and delicacy of cold, where motion is minimal and time seems to pause, offering a window into the underlying order of the universe. In the ultra-cold laboratories on Earth, researchers manipulate these states to explore superfluidity, quantum entanglement, and superconductivity, pushing technology and human understanding forward, all by studying matter at temperatures where the classical world ceases to behave normally. Imagine entire clouds of space dust, barely moving, influenced only by the faint tug of gravity and radiation, eventually coalescing over millions of years into stars, planets, and perhaps life itself. A process frozen in time yet containing the seeds of energy and complexity that will one day blaze as brilliantly as the stars themselves. This extreme contrast between cosmic heat and cold, chaos and stillness, demonstrates that the universe is not uniform, but a dynamic interplay of extremes, where the laws of physics reveal themselves in both violence and serenity, and where our own existence is a product of this grand spectrum. From the infernos of stellar cores and neutron star collisions to the delicate, near-static realms of interstellar voids and quantum condensates, the universe teaches us that extremes are not anomalies, but fundamental, defining features, shaping matter, energy, and the very structure of space and time. As we explore these extremes, we begin to appreciate not just the power and mystery of the cosmos, but the remarkable precision and balance that allows the universe to exist in all its diversity, from fire to ice, from chaos to order, and from unimaginable heat to near absolute zero. As we move beyond the mere spectacle of the universe's extremes, it becomes clear that these seemingly incomprehensible temperatures, both searing and freezing, are not just curiosities, but essential keys to understanding the fundamental workings of reality itself, revealing the hidden architecture that governs everything from subatomic particles to galaxies. Consider the blazing cores of stars, where the fusion of hydrogen into helium is not only the source of light and heat, but also the origin of the chemical elements that make planets, oceans, and life possible. Without these extreme conditions, elements heavier than hydrogen and helium would never form, and the universe as we know it, including our own bodies, could not exist. The supernova that erupt with energy so intense that they briefly outshine entire galaxies are more than destructive explosions. They are cosmic forges, scattering the heavy elements essential for planets and life across the cosmos. Similarly, the titanic collisions of neutron stars, creating temperatures in the trillions of degrees, generate gold, platinum, and other rare elements, which eventually become part of planets, jewelry, and technology, reminding us that even the most violent extremes have profound consequences for the tangible world around us. On the other end of the spectrum, the near-absolute zero regions of interstellar space, once thought to be empty voids, are quiet laboratories where the fundamental laws of physics reveal themselves in ways impossible to observe elsewhere. In these frozen expanses, quantum behaviors dominate, and subtle phenomena like the formation of molecular clouds and the slow coalescence of matter provide the raw material for future stars and planetary systems. The cosmic microwave background, lingering at just a few degrees above absolute zero, is a snapshot of the universe when it was only 380,000 years old, encoding information about its origins, composition, and evolution. By studying this faint glow, scientists can trace the expansion of the universe, the distribution of dark matter, and the seeds of galaxies that would form billions of years later. These extremes, therefore, are not isolated. They are interconnected threads in the tapestry of cosmic evolution, a continuous cycle where heat and cold, creation and dormancy, destruction and formation all coexist to shape the universe over eons. The study of these extremes has also transformed our understanding of physics itself, challenging established theories and pushing humanity toward deeper comprehension. When matter is exposed to trillions of degrees, as in particle collisions near black holes or in laboratory recreations of quark-gluon plasma, it behaves in ways that cannot be explained by classical physics, revealing the fundamental interactions that govern subatomic particles, the strong force that binds nuclei, and the mechanisms behind energy release on cosmic scales. At the opposite extreme, ultracold matter reveals phenomena like superfluidity, superconductivity, and quantum entanglement, where the classical rules of motion and thermodynamics break down, giving rise to entirely new states of matter and behaviors that have potential applications in quantum computing and advanced technology. These extremes are thus laboratories in their own right, one forged in fire, the other in ice, both providing insights into the laws that govern reality itself. Furthermore, the existence of these extremes underscores the delicate balance that allows the universe to function as it does. The cosmic thermostat, so to speak, ensures that regions of heat and cold exist side by side, creating the conditions for structure, stability, and evolution. Stars burn and die, scattering matter that forms new systems. Interstellar cold regions incubate future stars and planets. Black holes shape galaxies with their gravitational influence while conserving energy in ways that maintain cosmic equilibrium. This interplay between extremes is essential, a reminder that chaos and serenity, destruction and creation, are two faces of the same cosmic coin. In that understanding, one requires appreciation of the other. Beyond pure science, these extremes provoke a profound sense of wonder and philosophical reflection, confronting humanity with questions about our place in the cosmos. If matter can reach trillions of degrees or cool to near absolute zero, what does that say about the range of possibility in the universe? How does life emerge in a cosmos that operates under such violent and delicate extremes? And what can we learn about resilience, adaptation, the nature of reality itself by observing these phenomena? In laboratories on Earth, scientists manipulate ultracold atoms with lasers and magnetic fields to explore quantum mechanics, seeking to harness the strange behaviors revealed by extreme cold for practical purposes. From quantum computers that could revolutionize computing to materials that could transmit electricity without resistance. Meanwhile, astronomers use telescopes and observatories to study the extreme heat of stellar collisions and black hole accretion, seeking to understand energy generation, galaxy formation, and the limits of physical law. Every discovery at these extremes ripples outward, influencing technology, philosophy, and our understanding of the universe, showing that curiosity and exploration are as fundamental to human progress as fusion is to stars. Even in everyday life, the knowledge gained from studying extremes has practical consequences. The understanding of high-energy physics informs nuclear power and medical imaging. Low-temperature research advances superconductors and magnetic resonance technologies. In this way, the extremes of the cosmos are not distant curiosities. They are deeply connected to human civilization, revealing both the fragility and potential of life in a universe governed by forces far beyond our ordinary experience. Ultimately, contemplating these extremes is an exercise in perspective. The furious heat of a neutron star collision and the serene cold of a molecular cloud are not merely scientific phenomena. They are mirrors reflecting the scale, complexity, and beauty of the cosmos. They remind us that life exists in a universe of contrasts, that our existence is possible because of the interplay between fire and ice, motion and stillness, creation and dormancy. As we study these extremes, we are drawn into a deeper understanding of the universe. Every temperature, every energy state, and every quiescent void has meaning, purpose, and consequence. The violent and the serene, the blazing and the frozen, together narrate the story of existence itself, demonstrating that the universe is not only a realm of awe-inspiring spectacle, but also a profound teacher, guiding humanity to explore, understand, and marvel at the delicate balance and extraordinary diversity of cosmic extremes. By witnessing the extremes of temperature and energy, from the cataclysmic heat that shapes galaxies to the silent cold that preserves the memory of the Big Bang, we see the universe as a dynamic, interconnected system, where every extreme is a window into the laws of nature, a laboratory for discovery, and a source of inspiration, reminding us that in understanding the universe, we also begin to understand ourselves. As we draw our journey through the universe of extremes to a close, it is impossible not to feel both humbled and exhilarated by the sheer scope and diversity of cosmic phenomena that exist beyond our everyday perception, where temperatures soar to unfathomable trillions of degrees and plunge to near absolute zero. Yet both extremes coexist within a vast, interconnected tapestry of matter, energy, and space that stretches across billions of light years. Reflect for a moment on the stars, those blazing furnaces that dominate the heavens with their incandescent brilliance, where nuclear fusion in their cores releases energy at temperatures so high that matter itself is torn apart and reconstructed in cycles of creation and destruction, forming elements that will one day coalesce into planets, oceans, and life. Consider the violent deaths of massive stars in supernova explosions. Events so powerful, they release more energy in a single moment than our sun will emit over its entire lifetime, scattering the building blocks of matter into the surrounding cosmos, forging the iron in your blood, the calcium in your bones, and the gold that adorns jewelry, all of it birthed from fire hotter than anything we can truly imagine. And yet, in contrast, just a few light years away, the universe contains regions of astonishing stillness and cold, where temperatures hover mere degrees above absolute zero, and atoms drift in languid motion, barely interacting, preserving the faint echoes of the Big Bang and the cosmic microwave background. These frozen realms, invisible to our eyes, yet detectable by precise instruments, are laboratories of serenity, where the rules of quantum mechanics manifest in elegant ways. From Bose-Einstein condensates created in carefully controlled Earth, laboratories to interstellar clouds that incubate future stars over millions of years, demonstrating that even in silence and stillness, the universe is endlessly productive, orchestrating the next chapters of cosmic evolution. The interplay between these extremes is nothing short of miraculous. The searing heat of neutron star collisions, which briefly reaches trillions of degrees, forges rare elements and generates gravitational waves that ripple through space-time, while the ultra-cold vacuum of interstellar space preserves the memory of the early universe, ensuring that the story of cosmic evolution is written across both energy and inertia, fire and ice, chaos and stillness. This duality reflects a profound principle. The universe is not uniform, nor is it balanced in the conventional sense. Rather, it thrives on contrast, extremes, and the tension between opposing forces. And it is through this tension that complexity, structure, and life emerge. These extremes also illuminate the laws of physics in ways that are impossible to replicate under ordinary circumstances. Observing matter at the highest temperatures achieved in cosmic collisions or in particle accelerators reveals the fundamental interactions that bind quarks, gluons, and nucleons, exposing the nature of the strong nuclear force, the behavior of energy under extreme pressure, and the conditions that govern the earliest moments of the universe. Conversely, chilling matter to near absolute zero exposes the subtleties of quantum mechanics, revealing superfluidity, superconductivity, and the mysterious entanglement of particles separated by vast distances, a phenomena that challenge classical intuition and hint at the underlying unity of the cosmos. Humanity's pursuit of knowledge in both fiery and frozen extremes reflects an insatiable curiosity, a desire not only to witness the spectacle of the cosmos but to understand its principles and harness them for exploration, technology, and insight. The same forces that govern the heart of stars, the collisions of neutron stars, and the silent cold of interstellar space also guide experiments on Earth, from quantum computing and advanced materials to nuclear fusion and energy generation, demonstrating that the study of extremes is both a quest for understanding and a practical endeavor that shapes our civilization. As we contemplate the blazing heat and chilling cold of the universe, it is impossible not to reflect on our own existence within this immense framework. Our planet, our solar system, and even our bodies are products of these extremes, forged in the crucible of stellar processes and nurtured in regions cooled to near silence, reminding us that life itself is a delicate balance between energy and entropy, motion and stillness. The awareness of this balance fosters a profound sense of connection. We are participants in the ongoing narrative of cosmic evolution, observers and beneficiaries of processes that span billions of years and trillions of kilometers. A humbling perspective that places our daily concerns in a broader, almost philosophical context. Moreover, the extremes of temperature serve as metaphors for human experience, illustrating the interplay of intensity and calm, creation and dormancy, chaos and order. Just as the universe thrives on the tension between searing heat and freezing cold, our lives are shaped by contrasts, by moments of brilliance and periods of reflection, by bursts of activity and intervals of quiet contemplation. The cosmos teaches us that extremes are not to be feared or ignored, but studied, appreciated, and respected. because it is through understanding these forces that we gain insight into the fundamental nature of reality. In a deeper sense, witnessing the extremes of the universe cultivates a sense of wonder that transcends science alone. It inspires imagination, art, philosophy, and storytelling, prompting questions about existence, the origin of matter, the nature of time, and the possibilities that lie beyond our current comprehension. Each blazing star, each frozen void, each fleeting supernova, and each silent interstellar cloud is a reminder of the majesty of creation and the limitless potential of exploration. These extremes are also invitations, inviting humanity to dream bigger, to push technological and intellectual boundaries, and to seek knowledge even when it seems unattainable. They are challenges and opportunities simultaneously, demanding that we develop tools, instruments, and ideas capable of probing realms far beyond ordinary human experience. As our telescopes gaze into distant galaxies, our particle accelerators recreate the conditions of the earliest universe, and our ultracold laboratories manipulate atoms at temperatures almost devoid of motion. We participate in a tradition of inquiry that links past, present, and future, connecting generations of thinkers across the span of history. Ultimately, as we reflect on the universe from these extremes of heat and cold, it becomes evident that the cosmos is both violent and serene, chaotic and ordered, incomprehensibly vast and intimately connected to our very being. The fiery explosions that birth elements and shape galaxies, and the silent, frozen regions that preserve the universe's memory and incubate future stars, together narrate the story of existence itself, a story of balance, contrast, and interdependence. The extremes we have witnessed are not anomalies or curiosities. They are essential threads in the cosmic fabric, illustrating that every aspect of the universe, from the most energetic to the most still, contributes to the grand narrative of creation, evolution, and eventual transformation. And so, as we conclude our exploration, we are left not only with knowledge, but with all recognition that we inhabit a universe of staggering contrasts, where the unimaginable heat of stellar furnaces and the near-perfect cold of interstellar voids coexist in harmony, shaping matter, energy, and life in ways that are both profound and beautiful. The universe, in its extremes, challenges us, teaches us, and inspires us, reminding us that even as we reach toward the furthest stars or manipulate atoms in ultra-cold laboratories, we are forever connected to the grand cosmic story, a story of fire and ice, of brilliance and stillness, of chaos and order. A story that continues to unfold across the boundless expanse of space and time, inviting us to marvel, explore, and wonder at the universe of extremes in which we live. Asterisk. The universe of extremes is not simply a display of numbers or temperatures, but a profound testament to the diversity, complexity, and ingenuity of cosmic processes. A realm where the most violent forces coexist alongside the most delicate stillness, and where every scale of temperature, from the incomprehensible heat of neutron star collisions to the near-perfect cold of interstellar voids, tells a story about the origin, evolution, and destiny of everything that exists. Imagine for a moment the life cycle of a massive star, beginning as a dense molecular cloud cooled to near absolute zero, where gravity slowly pulls matter together over millions of years, so delicately balanced that even a slight disturbance could halt the process entirely. In these frigid clouds, atoms drift lazily, barely interacting, yet their slow motion and subtle interactions set the stage for the explosive drama to come. As gravity compacts the material, pressure and heat build within the nascent stellar core, until eventually nuclear fusion ignites, releasing energy at millions of degrees. A transformation from near-zero stillness to blazing inferno, demonstrating the extraordinary range of conditions required to produce light, heat, and eventually life. As the star matures, it burns steadily, fusing lighter elements into heavier ones, a process that shapes the chemistry of the universe. Yet, it is in the star's death that extremes are most apparent. In a supernova, the core collapses in an instant, Temperatures spike to billions of degrees, and matter is hurled outward at incredible velocities, seeding the surrounding space with heavy elements that are critical for the formation of planets, oceans, and life. In this violent moment, matter reaches conditions beyond comprehension. With atomic nuclei breaking apart and reforming, gamma rays streaming across space, and neutrinos escaping in numbers that outpace entire solar systems. Now, contrast this with the universe's coldest regions, where temperature hovers just a fraction above absolute zero. In these silent voids, the energy of matter is minimal. Atoms barely move, and quantum effects dominate. Here we observe the subtle beauty of a cosmos that is not all chaos and violence, but also patience, precision, and persistence. These ultra-cold regions are incubators for future stars and planets, demonstrating that even in stillness, the universe is alive with potential, and that extremes are complementary rather than contradictory. The fiery and the frozen exist together, shaping each other and the larger structure of galaxies, clusters, and cosmic filaments, creating a dynamic tension that drives evolution on every scale. Beyond these natural extremes, humans have begun to explore and recreate them in controlled environments, bridging the gap between observation and experimentation. In laboratories on Earth, physicists have cooled clouds of atoms to billionths of a degree above absolute zero, forming Bose-Einstein condensates where individual atoms lose their identity and behave as a collective quantum entity. In these experiments, time seems to stretch. Particles move in harmony, and phenomena such as superfluidity and entanglement emerge, revealing aspects of nature that cannot be observed at ordinary temperatures. At the other end, particle accelerators replicate conditions similar to those present just moments after the Big Bang, briefly achieving trillions of degrees and creating quark-gluon plasma, a state of matter that existed when the universe was less than a millionth of a second old. These extreme experiments are not merely curiosities. They are windows into the laws that govern reality itself, allowing humans to probe the limits of physics, test theoretical models, and understand the universe's origins in a way that observation alone cannot provide. The extremes also challenge our perception of scale, intensity, and time. In the hottest environments, processes unfold in milliseconds, yet they can influence entire galaxies over billions of years. In the coldest regions, motion is so slow that billions of years pass with almost imperceptible change, yet these slow processes lay the groundwork for the formation of stars, planets, and life. By witnessing both extremes, we gain a new appreciation for the interconnectedness of the cosmos, and for the delicate balance required for complexity to emerge. This balance is evident not only in matter and energy, but also in the cosmic cycles of creation and destruction. Stellar explosions and black hole activity redistribute matter and energy, while cold interstellar clouds gather, collapse, and reignite in new stars. Galaxies grow, collide, and merge, all under the influence of extremes, demonstrating that the universe's grand architecture depends on both violent energy and quiet inertia. Human curiosity mirrors this cosmic interplay, driving us to explore extremes both outward and inward. Telescopes capture the light of distant explosions, particle detectors sense fleeting quarks, and quantum experiments probe the behavior of ultra-cold atoms, revealing patterns and principles that inform our understanding of the cosmos and the technologies that shape our civilization. In contemplating these extremes, we also confront profound philosophical questions about existence, scale, and our place in the universe. If the cosmos can generate temperatures that obliterate matter and regions so cold that time seems suspended, how do we, as sentient beings, navigate this immense spectrum? What does it mean to exist in a universe where such contrasts are not anomalies, but fundamental features of reality? These questions inspire awe, humility, and a sense of wonder, reminding us that science is not only a tool for understanding, but also a lens through which we experience the sublime. The extremes of heat and cold are thus inseparable from human imagination and culture, inspiring stories, art, and philosophy, as well as technological innovation. Knowledge of high-energy physics informs nuclear energy and medical imaging, while low-temperature research advances superconductors, quantum computers, and ultra-precise sensors. In this way, the universe's extremes are not distant or irrelevant. They are intimately connected to human progress, demonstrating that understanding the cosmos is both a practical and existential endeavor. Furthermore, these extremes illuminate the remarkable resilience and adaptability of the universe. Stars survive for billions of years despite violent fusion reactions. Interstellar clouds persist in near-zero temperatures, and particles behave consistently under conditions that would destroy ordinary matter. This resilience reflects underlying principles of order, symmetry, and conservation, revealing that extremes are not chaotic in isolation, but part of a larger, coherent system where energy, matter, and forces interact according to universal laws. Even in apparent chaos, there is structure, and in stillness, there is potential. As we consider the full spectrum of temperatures from the searing plasma of stellar cores and supernova to the silent, frozen voids of intergalactic space, we recognize that extremes are essential to the story of existence itself. They define the boundaries within which matter, energy, and life emerge. They shape the formation of galaxies and planetary systems, and they provide the conditions for evolution on every scale, from atoms to civilizations. These extremes also serve as mirrors for human understanding, reflecting our limitations, our creativity, and our desire to explore, measure, and comprehend what initially seems incomprehensible. By pushing the boundaries of observation and experimentation, humanity engages in a dialogue with the universe, learning not only about stars, atoms, and cosmic history, but also about the principles of persistence, balance, and interconnectedness that govern all systems. The universe of extremes teaches patience and imagination, rigor and humility, demonstrating that even the most violent and most still conditions have purpose, beauty, and meaning. It challenges us to see beyond our immediate experience, to contemplate processes that span billions of years and trillions of kilometers, and to recognize our place within a vast, dynamic, and awe-inspiring cosmos. In embracing both the fire and the ice of the universe, we gain perspective, insight, and inspiration, understanding that extremes are not anomalies, but fundamental to the richness, diversity, and continuity of existence. As we continue to explore, experiment, and wonder, the universe invites us to witness its extremes, to marvel at the unimaginable, and to recognize that every blazing star, every silent void, every superheated plasma, and every ultra-cold atom is part of a grand narrative that connects us to the cosmos, revealing a reality that is as beautiful and intricate as it is immense and mysterious. A universe where extremes define not only matter and energy, but also the very nature of understanding, curiosity, and existence itself. In the end, contemplating the extremes of temperature, from the furious heat that shapes galaxies to the serene cold that preserves the memory of the cosmos, we are reminded that the universe is simultaneously violent and delicate, explosive and silent, unpredictable and governed by law, and that our journey through it, as observers and participants, is a testament to the extraordinary scale, power, and subtlety of all that exists. Asterisk.